Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation. The paper titled Unified Embeddings for Multimodal Retrieval via Frozen LLMs outlines a method known as Unified Embeddings for Multimodal Retrieval, UNIMR. This method aims to reduce modality bias in large language models, LLMs, and enhance the retrieval of multimodal outputs. The method consists of two main steps: image-to-text training and dual alignment training. Image-to-text training. This step is designed to map an image into the LLM input space, also known as the text space. The visual embedding of a given image is initially extracted using the CLIP visual encoder. A linear mapping layer is then trained to convert these visual embeddings into the LLM's input space. This process allows the model to translate visual inputs into language-like tokens that can be directly processed by the LLM. The mapping layer is trained using an image captioning objective, which generates text tokens within the textual caption conditioned on the visual prefix. Dual alignment training. This step trains UNIMR to retrieve multimodal outputs consisting of paired image text data. The LLM's last output embedding is mapped to a unified multimodal space using a linear mapping layer. This unified multimodal embedding is then aligned with both visual and textual semantics using a dual alignment training (DAT) method. The DAT method involves two training objectives: visual matching, VM, loss, and textual matching, TM, loss. Visual matching loss. This aligns the unified multimodal embeddings with the visual semantics provided by the CLIP visual encoder. The InfoNCE loss, a type of contrastive loss function, is used for this purpose. Textual matching loss. This aligns the unified multimodal embeddings with the textual semantics. A mean square error MSE loss function is used to minimize the L2 distance between the multimodal embedding and the textual semantics. During inference, UNIMR retrieves both visual and textual outputs using the trained unified multimodal embedding. The model first maps the image-to-text space via the image-to-text mapping layer and feeds the result to the LLM. The LLM's last output embedding is then mapped to the unified multimodal embedding. The model retrieves the most relevant multimodal candidates from the pool using cosine similarity. In conclusion, the proposed UNIMR method embeds multimodal inputs and retrieves multimodal outputs via frozen language models. It applies a dual alignment training strategy to jointly retrieve visual and textual outputs via a unified multimodal embedding. This significantly reduces the text-only response bias and retrieves multimodal outputs with increased cross-modal consistency. The authors conducted a series of experiments to validate their proposed method, UNIMR. The experiments were designed to evaluate UNIMR's performance on various multimodal retrieval tasks. Multimodal response retrieval. The authors compared UNIMR's performance to the recent FROMIG-E model on a multimodal response retrieval task. The results showed that UNIMR significantly reduced the text-only bias within the LLM output and outperformed existing methods on all metrics. Contextual image retrieval. The authors reported the zero-shot contextual image retrieval results on the Dialog dataset. UNIMR outperformed the baseline FROMIG-E approach, indicating that the unified multimodal embedding is capable of capturing important visual information for image retrieval. Dialog-to-image retrieval. The authors evaluated UNIMR on a dialog-to-image retrieval task on the Visual Dialog (VisStyle) dataset. This task tests the model's ability to embed complex contexts and retrieve the most relevant image given the dialogue context. UNIMR outperformed CLIP and FROMIG-E on all metrics, improving the R at 1 by 3.9% compared to the FROMIG-E baseline. Ablation study. The authors conducted an ablation study to understand the impact of different model design choices. They validated the effectiveness of the dual alignment training strategy in UNIMR and compared the different loss choices for their text matching training. The results showed that the regression-based objective performed better than the contrastive objective. Qualitative analysis. The authors provided some examples of UNIMR's retrieval results on the Dialog dataset. showing that Unimer is capable of embedding multimodal context and retrieving visual and textual responses. Additional evaluation tasks. The authors also evaluated Unimer on a visual question answering (VQA) task on the VQAV2 dataset. Unimer achieved better VQA results compared to the baselines. They also extended their method to multimodal generation by incorporating the dual alignment training to the recently proposed multimodal generation framework GIL. Their approach retained strong multimodal generation ability while having significant improvement on multimodal retrieval. These results provide strong evidence for the effectiveness of the Unimer method in various multimodal retrieval tasks. This is AI Research Radar. Now, we will be delving into the next paper on our agenda. The paper titled ScreenAI, a vision language model for UI and infographics understanding discusses ScreenAI, a vision language model designed to understand user interfaces, UIs, and infographics. It builds upon the poly architecture, incorporating the flexible patching strategy of Pix2Struct, and is trained on a unique mixture of datasets. The model identifies and describes UI elements, which aids in generating training datasets for question answering, QA, UI navigation, and summarization. ScreenAI's architecture is inspired by the Poly family of models, which includes a multimodal encoder block with a vision encoder like VIT and a MT5 language encoder. The input image is transformed into a sequence of embeddings by the vision encoder, which are then concatenated with the input text embeddings and fed into the MT5 language encoder. The output of this encoder is passed to the decoder to generate the text output. ScreenAI extends this architecture to accept various image patching patterns using a technique introduced in Pix2Struct. ScreenAI is trained in 3 different sizes containing 670M, 2B, and 5B parameters. The training process consists of 2 stages, pre-training and fine-tuning. During pre-training, the model is trained on large datasets generated from self-supervision and other models, using minimal human labeling. During fine-tuning, the model is trained on mixtures of tasks, most of which are labeled using human annotators. The pre-training phase of ScreenAI's development relies on automatic data generation. This approach leverages specialized smaller models, each adept at generating and labeling data both efficiently and with a high degree of accuracy. The cornerstone of the annotation process is a layout annotator based on the DTR detection model. This object detector identifies and labels a wide range of UI elements. Pictograms undergo further analysis using an icon classifier capable of distinguishing different icon types. An OCR engine extracts and annotates textual content on the screen. Finally, all these annotations are combined to create a detailed and holistic description of each screen, termed screen schema. ScreenAI uses 2 distinct sets of tasks, an initial series of pre-training tasks and a subsequent set of fine-tuning tasks. The pre-training tasks encompass a significantly larger quantity of samples and are used for training the model over a more extended series of steps. The fine-tuning tasks are labeled using human annotators and are used to estimate the quality of the model. The experimental work conducted to validate the methods in the paper is divided into several sections. Experiment setup. The VIT encoder is held frozen and only the language model is fine-tuned during the fine-tuning phase. The batch size for fine-tuning is set to 512 with an input sequence length of 128. The output sequence length varies depending on individual tasks. When fine-tuning with OCR as additional input, the input sequence length is increased accordingly. The model generally converges within 30K steps. All experiments are run on the 5B model. Results. The performance of the models is compared with state-of-the-art SOTA results on a variety of screen and infographics-related tasks. New SOTA results are reported on Motif, widget captioning, MP-Doc VQA, and WebSRC, and new best-in-class results in Chart QA, Doc VQA, and Infographic VQA, Info VQA. The results on the baselines introduced in Section 4.2, Screen Annotations, Referring Expressions, Screen QA Short, and Complex Screen QA, are also reported. Adding OCR as additional input. The impact of adding OCR to the model input is analyzed by conducting experiments with and without OCR. For QA tasks, adding OCR provides a boost in performance, e.g. up to 4.5% on complex screen QA, MP-Doc VQA, and Info VQA. However, using OCR imposes a slightly larger input length and hence results in slower overall training. It also requires having OCR results available at inference time. Model size: single-task experiments with the following model sizes, 670M, 2B, and 5B are conducted. The metrics improve consistently as the model size increases. For tasks that require more complex visual text and arithmetic reasoning, e.g. Info VQA, Chart QA, and complex screen QA, the improvement between 2B and 5B models is significantly larger than between 670M and 2B models. Ablation studies. Ablation studies are performed to evaluate the impact of PIX2 struct patching and using LLM-generated data for pre-training. All ablation studies are performed on the 670M parameter variant. The impact of PIX2 struct patching is evaluated by comparing a 670M model using PIX2 struct patching with another using fixed grid patching. The impact of using LLM-generated data for pre-training is evaluated by comparing a 670M ScreenAI model pre-trained using all the datasets mentioned in Section 4.1 against a model pre-trained on a mixture excluding any LLM-generated pre-training data. New benchmarks and datasets. 3 new evaluation datasets are released for tasks described in Section 4.2, Screen Annotation, Screen QA Short, and Complex Screen QA. These datasets enable the research community to utilize the textual representation and allow for a more comprehensive benchmarking of models for screen-based question answering. This is AI Research Radar. Now, we will be delving into the next paper on our agenda. The paper titled Enabling Large-Scale Screening of Barrett's Esophagus Using Weakly Supervised Deep Learning and Histopathology presents a weakly supervised deep learning approach for large-scale screening of Barrett's esophagus using histopathology slides. The approach aims to improve screening capacity and reduce the workload of pathologists. The study used 2 datasets, the discovery dataset and the external test dataset. The discovery dataset consists of 1,141 cases with both hematoxylin and eosin, HNE, and trefoil factor 3, TFF3, stained whole slide images from patients in the Delta implementation study. The external test dataset consists of 725 cases with HNE slides from the best 2 clinical trials. Pre-processing was performed to mitigate undesirable artifacts, standardize background effects, and to remove control tissue in TFF3 slides. The study used a weakly supervised deep learning model called BTransMIL. The model is composed of 4 main components: a feature extractor, a dependency module, an attention MIL pooling module, and a fully connected classifier layer. The feature extractor encodes each image tile into lower dimensional feature maps. The dependency module captures spatial dependencies between individual tile maps in a bag into compact vector representations. The attention MIL pooling module uses a multi-layer perceptron, MLP, with a single hidden layer of dimension 2048. The fully connected classifier layer receives a linear combination of all tile embeddings weighted by attention values to compute the final probability to predict a label for the slide. The models were trained using binary cross-entropy loss using solely slide labels. Hyperparameter tuning was performed for high specificity so that the models could confidently identify negative cases automatically. For training the models, a batch size of 8 slides was used. Learning rate was fixed at 3 times 10⁻⁵ with a weight decay of 0.1, and models were trained for 50 epochs. Due to unbalanced datasets, class reweighting was applied using the scikit-learn library. For qualitative analysis, attention heat maps were plotted overlaid on the slides. For each tile, the attention values were color-coded based on the reversed spectral color map. The tiles with high and low attention values were visually investigated. To quantify whether the high attention tiles of the learned models correspond to tiles with high TFF3 expression, a detailed analysis was performed. The reference TFF3 tissue crops were spatially registered to the corresponding H&E crops. The hematoxylin images were then registered with an affine transform followed by a coarse cubic B-spline deformation, optimizing a mutual information criterion using simple ITK. The model agreement of H&E and TFF3B trans-MIL models on their false predictions, false positives, FPs, or false negatives, FINs, was computed. This was computed as the jacket index, intersection over union, of the sets of false predictions made by TFF3 and H&E models independently. The study analyzed the performance, sensitivity, specificity, and the requirement for pathologist review and TFF3 stain for multiple combinations of H&E and TFF3 models, as well as pathologist, leading to 14 different ML-assisted workflows. The workflows were designed to optimize specificity, to enable pathologists to review fewer negative cases and focus on the high-risk cases. Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.